Okay, so the next concept we're going to take a look at is what we call drip rate or drop rate. So drip rate is how many drops per minute an infusion is running. Okay, and that is not to be confused with what we call the drop factor, which is how many drops are in each mil. Now, the drop factor is going to just be based on the type of IV tubing that you're using. So we can have bags that do macro drips, which are very large drops. So there's going to be less drops in each mil. Or we can have a micro drip, which is going to have a lot of tiny drops here. So if you look at your book on page 420, there's a good reference of an example of each of these here. So here we can see that we have a macro drip. So the drips are much larger. So there's only 10 drops per milliliter running in this bag. Whereas this bag is a micro drip. So we have very tiny drips running. There are actually 60 drops in every 1 milliliter in this bag. So once again, that is called a drop factor, and that is dependent on the type of tubing that we're using. Now, your drop rate or your drip rate is how many drops are running per minute. Remember, a rate is an amount per time. So I think the easiest way to start getting into some of these problems is to just take a look at some examples here. So in some of these problems, we may need to use the drop rate or the drip rate to find the total volume that an IV will be providing, or we could be looking for the flow rate or the drip rate, which is drops per minute. Or we could be looking for the time it takes for the IV bag to infuse. Usually the calibration is always given to us because that is going to be what is on the IV tubing. So let's take a look at number 7 on the worksheet here. Now with these drip rate problems, almost all of these we're going to have to use dimensional analysis. So number 7, a physician orders metronidazole 750 milligrams in 500 mils of normal saline to run for 4 hours. Calculate the drip rate if the drop factor is 50 drops per mil. So, dimensional analysis. We know that drip rate is always drops per minute. So let's start with what we want to find. Follow that up with an equal sign. Now, the next step is to take the information that we're given, and we want to have drops on top of our first fraction here. So we know that the drop factor, there are 50 drops in every 1 milliliter. So there's 50 drops in every 1 milliliter. Now, the next thing to do, set up your next fraction to where your numerator here is the same as your denominator of the first fraction. So we want to have milliliters up top. The only thing we know about milliliters that's given to us is that our bag is 500 milliliters total. So there's 500 mils in our bag. So right away, I know my mils are going to be canceled out, and I'm going to be left with drops on top, but I want to have minutes here on the bottom. So I want to find something relative to time so I can plug in my minutes here. So reading through here again, I know that this is running for 4 hours. So that is in hours. I want that to be in minutes because that's what I'm looking for. So let's go ahead and convert this hours into minutes. So we know that 1 hour is 60 minutes. So 4 hours, 60 times 4 would be 240 minutes here. So now I know that this bag bag is running for 240 minutes. When I'm left with the units that I want, drops per minute, then I can solve. So we'll just put that to the side there. So now, multiplying fractions, always multiply straight across. So 50 times 500 gives me 25,000. And then 1 times 240 is just 240. So 25,000 divided by 240 leaves me with 104. And in my calculator, I got 104.16. So we can't really round a drop to the nearest decimal. So we're just going to leave it at the nearest whole number. So 104.16 would be closer to 104 drops per minute, the only units that I have left. So we can see here in this problem, we didn't even need to worry about this metronidazole 750. That just wasn't important. They're just throwing in information that we don't need. Okay, so always start with what you're looking for. Make sure your first fraction has the same numerator, and then make sure your second fraction has the numerator that will match the denominator of the first fraction. That way that they will cancel out. So what I'd like you to do now is go ahead and try out number 8 on your own. It's very similar to number 7. Use that as a reference. Okay, let's take a look at number 9. A physician orders lactated ringers in 500 milliliters to be infused at 30 drops per minute with an infusion set of 40 drops per mil. What is the infusion time in hours and minutes? So here we are looking for time in hours and minutes. So let's look at what I know about time that I'm given. I know that there's 30 drops in every 1 minute. So let's go ahead and first just solve for minutes, because that is the only thing that we know right now, and then we can go back and convert it into hours and minutes. So anytime you're using dimensional analysis and you're just looking for 1 unit, we need to make sure that that unit stays on top of any of these fractions that we're using here. So if it helps, you can just put that over 1, so we know that it needs to stay on top here. So always start your first fraction with that unit on top. So looking at our information here, we know that there's 30 drops per 1 minute. So I want my minute on top, so I can flip this around. I know that 1 minute, in 1 minute, 30 drops are running, okay? So now, next step, set up the next fraction to where the numerator here matches the denominator here. So I want drops on top. I've already used drops per minute. So the only other thing I know about drops is 40 drops per 1 milliliter, which is my infusion set or my drop factor. So I have 40 drops in 1 milliliter. So I've used that one now. When my drops will cancel out, I'll be left with minutes per milliliter, right? I only want to be left with just minutes, so I need to somehow cancel out this milliliters. The only way to do that is to use another fraction that will have milliliters here on top. So the only other thing that I'm given about milliliters is my bag that is 500 mils in total. So if my bag is 500 mils, my mils are going to cancel out. This is by itself. There's nothing attached to this. It's just a total of 500 mils. So if it helps, you can use a placeholder of 1 to just put that so it stays in the numerator, because anything divided by 1 is still itself, right? So this still has a value of 500. Now my milliliters can cancel out. And now the only unit I'm left with is minutes, which is what I need, so I can go ahead and solve. So here we're going to take 40 times 500, which gives me 20,000. And then 30 times 1 is just 30. So 20,000 divided by 30. I'm going to round this to the nearest minute. I'm getting 667 minutes. Now remember, they want our time in hours and minutes. So what we can do here, we know that there are 60 minutes in an hour. So we can just take this number here, 667, and divide that by 60, and that will turn our minutes into hours. So 667 divided by 60 minutes per hour equals, I get 11.12 hours. Now remember, if I say that'll last 11.12 hours, that's not going to make sense. And this also does not mean 11 hours and 20 minutes. Okay, this is just in hours right now. So we know this is 11 whole hours. So 11 hours. And then once again, to convert a decimal in hours into minutes, or back into minutes in this case, remember we can multiply this by 60. So 0.12 times 60, that gives me roughly 7 minutes. Comes out to 7.2. We'll just round to the nearest minute here. Now we can see if this makes sense by checking our work, right? We know 11 hours, if we change that into minutes, 11 times 60 would give us 660. And then we would have 7 minutes left over, right? So 667 minutes is equal to 11 hours and 7 minutes. So that is our final answer there. Once again, I apologize. I know that's pretty small. So calculating infusion times, that's what we just did. I just wanted to draw your attention to this slide here. So sometimes doctors will give an order without telling us how long that bag will last. So that's a case in which we would need to do a calculation like we just did. That way we can know when the next dose is ordered, so we can have that bag ready. So with the examples that we just went over, you should now be able to go through practice problem C. All of practice problem C is focusing on calculating drip rates. And I think I misspoke on the last video. You should also be able to go through practice problems B based on the first video that you watched as well.